Welcome to Ask and Learn.
Here we're going to be looking at the work done by a gravitational field. The field is a vector field, and it is a constant vector field that points 2 units of newtons per kilogram in the x direction and 3 in the y. So we want to find the work done by this field, and the work done is the line integral of force and displacement dotted into displacement. So typically we need 2 points to calculate the work between, we'll just say point A and point B. And the force, so writing the field as E rather than G for gravity, lets us know that the gravitational field is very similar to the electric field, is that the force on a test charge, little test charge, M, is simply M times that E. Okay, so we can simply put the electric field into our work relationship. And we're going to go from x1, y1. Let's spell out the points a little bit more to x2, y2. And the m comes out, assuming it's a constant mass. But we have ex dx plus ey dy. Okay, and in general, you have to be given some specifics about that field. Here, we're just told it is constant. So we have m times 2 dx let me put the points up there in the limits, and plus 3 dy. Now we can turn this into a single integral over one variable. So notice that there's a dx and a dy in there, and there are separate limits for those. So we could do this integral, but what we want to do is take a path rather than straight along the x and then along the y. Take a path such that it's on the line defined by 3y plus 2x is equal to 5. And typically what you do there, this is a parametrized curve. So what you want to do is simply figure out how to specify one variable in terms of the other. And that's easy to do. 5/3 y is equal to 5/3 minus 2/3 x. And then you can simply replace the dy with the differential element from your line. Okay, 2/3 x, that's not in the denominator, of course. There. Okay, so if we use that back up in the integral, note what happens is that your work done is equal to m. And here, since you're just looking at along the line and replacing y, you're going to go from x1 to x2. And that is 2 dx minus, oops, I forgot my differential up there, minus 2 dx. And that is 0, no matter what your endpoints are. Okay, so it kind of pays to think through why it came out to be 0. And really, the idea is that the tangent to the line is perpendicular to the E. Okay. Tangent vector to the line. So it's like you're moving the particle along an equipotential. That's sometimes called an equipotential line. And it supposedly takes no work and thus no change in potential energy if you move along an equipotential line.